Welcome to Foundation Mathematics, Logic. Logic, set theory, proof, connectives, and truth tables. The objectives for this session are to describe the relationship between propositional logic and set theory, recognize logical connectives and produce the truth table for them, and assess the equivalence of two propositions using simple logic. The notion of sets can help describe or define some properties of mathematical functions. We will explore the relationship that sets have with logic. In particular, we will look at propositional calculus, which is the most fundamental form of mathematical logic. The rules of logic can inform the process of research and can help make clear what can and cannot be inferred from a particular result. Propositional logic deals with propositions which can be true or false. It also deals with relations between propositions. This could include the construction of arguments based on them. Compound propositions are formed by connecting propositions by logical connectives. We're going to talk about these later. But first, let's take a look at an example. Statement 1. All children are good. Statement 2. Sarah is a child. From these two statements we can conclude that Sarah is good. This logical form is quite powerful, but often misused. What if one of these statements isn't true? We can only be certain that Sarah is good if all children are genuinely good, and Sarah is really a child. So what happens if one or more statements is false? What can we say about Sarah then? In order to examine this kind of question, we need to develop a whole new type of algebra, one that can cope with these types of questions. In algebra, order of operations such as plus and times is important. Similarly, in set theory, the order in which we use union and intersection is also important. Boolean algebra is concerned with only two possible values, or states: true and false, or 1 and 0, or yes and no, and so on. Let's take a look at an example. Consider the Boolean value of the following statements. Statement 1. My son went to school today. Statement 2. You have black hair. And Statement 3. My teacher's neighbour has a pet python. There is no uncertainty in these statements. We may not be aware of the truth or otherwise of a statement, but one of the two conditions must hold. In logic, we need other symbols to help work out whether a statement can possibly be true or not. The set of symbols for this is called connectives. We can use them to work out when a series of statements can lead to something else being either true or false. Suppose we have a statement P. It is either true or false. If P is true, then we can say that not P must be false. Conversely, if P is false, then not P must be true. Not P is represented by the symbol shown on your screen. Here's the truth table for not P. So if P is true, then not P is false, and if P is false, then not P is true. In set theory, the shaded area on your screen represents a to the power c or a complement, i.e. not a. Now let's take a look at the AND connective, P and Q. Suppose we have two statements, P and Q. For example, P equals I'm male, Q equals I was born in Mauritius. For U, none, one, or both of these statements will be true. Logic allows us to test whether a combination of these statements can be true. There are 4 possible combinations of truth here. We use the AND connective, which has the symbol of an upside-down V, to test which are true. In set theory, the shaded area on your screen represents A intersection B, or A and B. Here's the truth table for P and Q. So if P is true and Q is true, P and Q is true. If P is true and Q is false, then P and Q is false. If P is false and Q is true, then P and Q is false. And finally, if P is false and Q is false, then P and Q is false. Let's now consider the OR connective, P or Q. Suppose we have 2 statements, P and Q. If one of the statements is true, but not both, this is known as the exclusive OR. The inclusive OR is where one or both of the statements are true. In set theory, the shaded area shown on your screen is A or B, or A union B. Here's the truth table for P or Q. So if P is true and Q is true, then P or Q is true. If P is true and Q is false, then P or Q is true. If P is false and Q is true, then P or Q is true. And finally, if P is false and Q is false, then P or Q is also false. Now consider this question. How would we present the exclusive OR using the connectives we do know about? So let's now take a look at the exclusive OR. In set theory, the exclusive OR is represented by this shaded region. So we have A shaded and B shaded, but not the region representing A and B. So remember, either statement in logic must be true, but not both together. One way of representing this exclusive OR is P or Q and not P and Q, as shown here. You could use the diagram to help you understand how we arrived at this. So notice at the start of the statement we have P or Q. So in our diagram we have A or B. This A or B, or this P and Q, has to be intersected with the not P intersect Q, or the common region. And this gives us the shaded region in the diagram. Remember that the exclusive OR is only true if either statement is true, but not both together. So, if P and Q are both true, then the exclusive OR must be false. If P is true and Q is false, then the exclusive OR is true. Similarly, if P is false and Q is true, then the exclusive OR is true. And finally, if both P and Q are false, then the exclusive OR is also false. Let's now see if we can prove this using the connectives we do know about. We're going to use this table on the right-hand side of the screen to show this. Here's P or Q. We can find this out, or we can find out the truth statement for this using what we do know. Similarly for P and Q. Similarly for not P and Q. And once we've found out all of these, then we can find out the final statement's truth values and then compare them to the table we already have. Notice that we also have all possible combinations of true and false for the two statements P and Q. So let's proceed. We're going to create the truth table for the exclusive OR using the connectives we know about. So let's begin with P or Q. Notice that the values for P and Q are the same in both tables. So the truth values for P or Q must be the same also, as highlighted here. Now let's consider P and Q. Here's the truth table for AND. This also is translated into our new table. Now let's consider the NOT connective, so not P and Q. Here's the NOT connective truth table. So, if our statement is true, then negating that statement is false. Similarly, if our statement is false, then not of that statement is true. And so we have these truth values for not P and Q. Let's now take a look at the final column. This column requires the AND connective to connect the final statement. Here's the AND connective truth table. For a true and a false statement, the AND connective gives us a false statement. For a true and a true statement, the AND connective gives us a true statement. For a true and a true statement, again, the AND connective gives a true statement. And finally, for a false and a true statement, the AND connective gives a false statement. So here's our complete truth table for the exclusive OR. Let's now compare this to our original table. Notice that the truth values all correspond. False, true, true, false. And of course P and Q truth values are all in the same order in both tables. Now let's take a look at when we have more than two statements. Consider these statements. G equals I only eat gluten-free food. T equals I'm older than 20. And M equals I like maths. Now write out the meaning of the following statements shown on your screen and decide whether they are true or false when applied to you. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at part A first. G or T. This means I only eat gluten-free food, or I am older than 20, or both. Now for part B, T and M. This means I'm older than 20 and I like maths. Part C, not M or G. This means I don't like maths or I only eat gluten-free food, or both. And finally, G or T and not M. This means I only eat gluten-free food, or, and then in brackets, and the brackets are important here to show the order in which the operations need to be carried out, I'm older than 20 and I don't like maths. Now construct the truth table for G or T and not M. Pause the video and have a go. Press play when you're ready to view the solutions. So let's take a look at this. We have the headings for our truth table, not M, T and not M, and in the centre, G or T and not M. We also have all possible combinations of true and false for the three statements. Not M uses the not table. So all the true values, when negated, become false, and all the false values become true when negated. Now for T and not M. For this we need the AND truth table. So true false gives us false, true true gives us true, false and false gives us false, false and true gives us false, true and false gives us false, true and true gives us true, false and false gives us false, and false and true gives us false. And finally for the G or T and not M column. For this we need the OR connective. Here's the OR truth table. So we have true or false gives us true, true or true gives us true, true or false gives us true, true or false gives us true again, false or false gives us false, false or true gives us true, false or false gives us false, and finally again false or false gives us false. Let's now take a look at the if-then connective. Statement P implies statement Q. I find it generally easiest to understand this connective using this example. Let C equal the statement it is cloudy and let R equal the statement it is raining. This could be represented using set theory. So the cloudy region or the cloudy set, or it is cloudy, encompasses the it is raining set. In other words, if it's raining, then it must be cloudy. Let's now take a look at the truth table for this. If it's raining and it's cloudy, then R implies C is true. If it's raining and it's not cloudy, then R implies C is false. If it's not raining and it is cloudy, then R implies C could be true. We always err on the side of caution here, so go for the true statement rather than the false statement. It could also be false, but we err on the side of the truth. And finally, if it's not raining and it's not cloudy, then R implies C is also true. Now let's take a look at constructing a truth table for a more complex statement involving the if-then connective, P implies Q. We are required to construct a truth table for the statement P and Q implies not P or Q. Pause the video and have a go. Press play when you're ready to view the solution. So let's solve this. We have P and Q truth values as shown on the left-hand side. And we also have the headings of the table. P and Q, which is the left-hand side of the statement. Then P or Q, which is on the right-hand side of the statement. We then negate it as shown here. And finally, the statement in the centre connects the two parts, as shown here. Let's take a look at P and Q first. P is true, Q is true, P and Q is true. True, false gives us false. False, true gives us false. And false, false gives us false. Now for the column P or Q. True, true gives us true. True, false gives us true. False, true gives us true. And finally, false, false gives us false. For not P or Q, we simply negate each statement. So if P or Q is true, not P or Q is false. Similarly here, and similarly here. And of course, if P or Q is false, then not P or Q is true. Finally, let's take a look at the if-then part of the statement. Here's the truth table for if-then. So if we have true and false, then this is false. If we have false and false, then this is true. If we have false and true, then this is true. And if we have false and false, then this is true. And so we have the complete truth table. Now let's take a look at the equivalence connective, P if and only if Q. The equivalence connective is often used to show when two statements mean the same thing. It's sometimes described by the phrase if and only if, or IFF. Let's take a look at the truth table. P and Q are both true is true. P is true and Q is false, then P if and only if Q is false. If P is false and Q is true, then P if and only if Q is false. And finally, if P and Q are both false, then P if and only if Q is true. Let's now take a look at De Morgan's laws. Here's A complement in set theory, and here's B complement in set theory. Notice that this region represents A complement union B complement. Notice also that this is the same region as A intersect B, all complemented. In logic, this is analogous to the statement shown towards the bottom of your screen. Not P or not Q, if and only if not P and Q. We're going to produce a truth table for this statement. Here's the truth table set up to help us begin. P and Q are given on the left-hand side as usual, and the first row gives us the headings, as shown here. We have not P, not Q, not P or not Q together, and from the right-hand side, P and Q, negating this, not P and Q, and finally the complete statement. So let's proceed. Not P is as shown. So the trues become falses and the falses become trues since we're negating. Similarly for not Q here. So true becomes false and false becomes true. Not P or not Q means at least one has to be true. And now for P and Q, both have to be true together. Negating each of these again, T becomes F, or true becomes false, and false becomes true. And finally, the connecting statement. Here we have the if and only if statement in the center. And here's our complete truth table. Let's now take a look at another of De Morgan's laws. Here's A complement in set theory. Here's B complement in set theory. Here's A complement intersected with B complement, which, as you can see, is also A union B complement. Notice that this is analogous to this statement in logic towards the bottom of your screen. Not P and not Q, if and only if not P or Q. Now let's set up a truth table for this. Pause the video and have a go. Press play when you're ready to view the solution. So here's an almost empty truth table to help us get started. We have the values of P and Q, or the truth values of P and Q, on the left-hand side, and the appropriate column headings. Here are the truth values of not P and not Q, and then not P and not Q. Here are the truth values of P or Q, and then not P or Q. And finally, for the if and if statements, let's use our truth table for P if and only if Q. So notice that if both parts of the statement are false, then the connecting statement, or the statement connected by if and only if, is true. Here again, false false gives us true, and false false gives us true again. Finally, if we have two true statements, then when they're connected by if and only if, then that statement is also true. We now take a look at some rules for propositional logic. Let's discuss this first. Inference is not the same as implication. Let's examine this statement. If we state P, a statement, and then also state if P then Q, we have what we call an implication. If we state P, we can also infer Q. Let's examine this. This can be summarized as P implies Q, this is the implication part, or P therefore Q, and this is the inference part. Let's take a look at an example. If we let P equal the statement, my sibling is between 6 and 7 years old, and let Q equal the statement, my sibling is a child, then clearly P implies Q. In other words, if my sibling is between 6 and 7 years old, then my sibling is a child. However, we can also infer Q. So in other words, we can say it in a different way and say, my sibling is between 6 and 7 years old, therefore my sibling is a child. Suppose Q is not true. In other words, my sibling is not a child. Then clearly P won't be true either. In other words, my sibling isn't between 6 and 7 years old. In notation and using inference, we can write this as not Q, therefore not P. There are other rules besides the one we've just looked at. Some of these have been summarized here in this table. So the first one we've just looked at, P implies Q, that's the implication, and the inference is not Q, therefore not P. If we have P or Q, then we can infer not P, therefore Q, because either P is true or Q is true. So, of course, if P is not true, then Q must be true. If we have P implies Q, and if we also have Q implies R, therefore we can conclude that P implies R. And finally, for this table, if we have P implies Q, then we can infer, or we can say therefore, not Q implies not P. What about equivalence? If we have the expression P, this is the same as saying not P, a double negation. P is also logically equivalent to P and P. It's also logically equivalent to P or P. P and Q is logically equivalent to Q and P. This is, of course, the commutative law. Similarly, P or Q is equivalent to Q or P. We also have the associative laws. P and Q and R is equivalent to P and Q and R. We also have P or Q or R is equivalent to P or Q or R. We also have the distributive laws here and here, and finally the expanded equivalence, as shown towards the bottom of your screen. Let's now start to round up this session. This was all actually a short introduction to a particular form of mathematical logic. However, it is limited. For example, how would you test the statement, "Unless I work hard, I will fail my exam"? We could start by defining the statements. So let W equal "I work hard" and let F equal "I will fail my exam." Let's consider how we can write this in logical statements, or let's see how we can write "Unless I work hard, I will fail my exam" as a logical statement. Consider this, not W, in other words, I do not work hard or I will not work hard, implies F, implies I will fail my exam. This may be saying the same thing as "Unless I work hard, I will fail my exam." We could also possibly write this as not W, a double negative, so it's actually the same as saying W, which means I work hard, or F, or I fail my exam. So W or F, I either work hard or I fail my exam. Predicate logic uses a more complicated structure. Let's consider these examples. Statement 1. For all x, if x is a child, then x is good. We can write this as follows in these symbols. For all x, the upside down A represents for all. C of x, where C of x means x is a child, implies G of x, where G of x means x is good. Now let's take a look at statement 2. There exists an x who is a child and is good. We can write this as there exists an x, this reversed capital E means there exists. So there exists C of x, in other words, x is a child, and G of x, which means x is good, or the child is good. These extra symbols make predicate calculus very powerful, but also much more challenging. The issue with this logic is that quite often our choices are informed by our experience, or probabilities of something taking place. Predicate logic does not use these. However, fuzzy logic, which is used in logic for computing, does. This brings us to the end of this session. If you have understood its contents, you should be able to describe the relationship between propositional logic and set theory, recognize logical connectives and produce the truth table for them, and assess the equivalence of two propositions using simple logic. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.